Hi, this is the Physical World, Lecture 21, and it covers topics from Chapter 14 and 15, mostly mechanical waves, electromagnetic waves, sound waves, and some other smaller topics. And I will be attaching the link here when I'm done, every time I finish a lesson. So last time we talked about those topics, and today it's a bit of continuation of the same topics and a few more new topics. So first, let's talk about interference of waves. So what happens when waves meet waves? So in space, we can have more than one wave at the same time, at the same location. And when that happens, they interfere either constructively or destructively, or we have some kind of interference pattern. So suppose we have this top diagram here, and we have two waves happening to be at the same location, and they happen to be identical. So it turns out that every single point of a wave would just add up to give a resultant wave. So really what's happening is this disturbance in space or medium. Those disturbances add up. So those displacements, for example, let's consider this point here. So displacement for that point is whatever that number is, and the other wave has that displacement, which is corresponding to the same location, and those two displacements add up. So this value plus that value would give this value, and this would be a point corresponding to this point of this point in medium. Amplitude of the first one and the second one would add up, and whatever the sum of those two are will be the resulting amplitude. So it should be about double the height. And those points where the displacement was zero anyway would result in zero displacement as well. And if we map those points individually, we will get this resulting wave. And we can see that this is a constructive interference, and in this case we have double the amplitude but the same wavelengths of the waves. And we could also have a destructive interference, in which case this second diagram here shows destructive interference example. So in this case, this positive displacement and negative, so this positive distance is positive here, let's say 3 centimeters. And if we add this negative 3 centimeters to it, they give zero as a result. Or we could think of it as they cancel each other out. So this point cancels this point out, and we will have no wave at all. And this is really how, for example, noise cancelling headphones function. We can have all headphones more or less cancel the noise from surroundings, but noise cancelling headphones are designed to have a microphone in it, for example, and this microphone, I'm guessing it's detecting somehow this incoming wave from surrounding and creating a wave. So let me do it in different color. A wave that's maybe shifted by some amount so that it's canceling the incoming wave, and eventually we get no wave. So interference of waves is what's happening here as well. Let's talk about a few examples. So the top example, we more or less consider the second example here. So those two waves add up to give every point on the wave adds up, and we have a resultant wave with double the amplitude and the same wavelength. And the second one, we would have every single point is cancelled by a corresponding point on the other wave, and we will have a resultant wave that's basically like that. or no wave. In principle, almost. So in the first example, we will have this dotted line and solid line representing waves. And if we add those up, again, we talked about this. Let me first draw a straight line here, equilibrium position. And then if we add up, for example, those 2 points to each other, we will get the distance. So here is corresponding resultant wave. Superposition of those 2 points will give me about this point. Those nodes would add up to give nodes as well, so they would just remain at the same location because 0 plus 0 is 0. And that's negative displacement here, and the other one also has negative displacement, so resultant displacement of the medium would be here. So as a result, we will get a wave that's something like that. How about the second example? Well, because here they gave us numbers as well, probably they want us to draw it to scale. So let me check that it's correct. So 1 plus 1 is 2, so yeah, it's correct. And negative 1 plus negative 1 is negative 2, yeah. And let's do the second one to scale as well, and let's pick a different color, green. So first I want to draw an equilibrium line like that, and then I see that this distance here is 1 and that distance is negative half, so 1 plus negative half would be half. Those nodes would remain to be nodes, and this is an interesting point as well. So 1 half at negative 1 would be negative half, so we would have something like this. So this green wave represents a resultant wave, or superposition of those 2 waves. So as a result of interference, we'll have this green wave. Okay, so next let's talk about standing waves. If I have a rope attached to a wall, this is a wall and this is a rope, and suppose I'm holding on to one end, to the left end of this rope or a string. Now, if I oscillate it up and down at a certain frequency, at any frequency, it will just give me random waves, and I wouldn't see any pattern at all. But if I happen to oscillate this wave to be source, to give, to make a wave with a certain frequency, that is called, for example, fundamental frequency, I will be able to make a standing wave, and it will look something like this. So this wave that's going forward will have such a wavelength which would be exactly half of the total wave, because if I carry on, this will be total wave. So this distance, total waves, distance half would be this distance from here to here. So if I have this specific wavelengths or frequency as well, I will have a first possibility for the standing wave. So what happens is that the reflected wave that's coming backwards from the wall interferes with the wave that's going forward, and this result of interference of those 2 waves would look like a standing wave. I will try to attach a video on this because it's nice to see that, to visualize what's happening, and also we are not able to perform experiments since I cannot do that in the lecture. I will maybe find a video that shows all of that. And you can see, maybe this diagram might help as well a bit. A second wave that's like that would be when we have, maybe I should erase the first one. So I will do it in black. So this is my rope. And if I manage to oscillate at a frequency that is double the previously picked frequency, fundamental frequency, I will actually have a wave that's like that. So one wave going forward is reflected from the wall, and it's going back in such a way that it interferes with original wave. And because its wavelength happens to be just right, it will interfere constructively and make a standing wave. So let's consider this diagram here. So this is a person oscillating the wave. So this is the wave that's going forward, and the reflected wave is also coming back and constructively interfering with this one in this case, and we will have a wave that's double the amplitude. But at an instant later, we will see that we will have this wave is moving forward, so we will have this situation here, and then we will have those two waves destructively interfering, so they cancel each other out, so we will have no wave at all. And then if we wait for a bit longer, then the forward wave looks like this, and the wave that's coming backward, the dotted line, would again constructively interfere. So we again see the formation of the wave, and this is the resultant wave. That's result of constructive interference of forward and backward waves. And this keeps happening all the time. So we constantly see this. So 1 second we see that, another second we see that, and instant later we see that, and then it goes back and we see something like that. But those nodes would always stay at the same spot, because the wavelengths of the original wave or frequency of the original wave was just right, and we were able to fit one whole wave in this distance. And this could carry on for different frequencies. So remember, fundamental frequency was something like when we picked the perfect wavelength or frequency for the oscillation of the end of this rope. That was about the wavelength of that was about half of the double the distance between me and the ball, and this worked if this wavelength is exactly equal to the distance from me to the ball. So if distance between me and the ball is also equal to the wavelengths with which I'm oscillating it, or whatever the corresponding frequency is, then I have a standing wave. I will have a standing wave as well if I have 1.5 wavelengths fitting into this distance that's between me and the ball. So it turns out that whatever the fundamental frequency is, every multiplier of that, so 2 times fundamental frequency, 3 times fundamental frequency, all of those quantities would, if I happen to oscillate this and at those frequencies, I will still have a standing wave. And yeah, I won't be asking any quantitative questions on those. It's just nice that you maybe visualize what's happening. So I will try to find a video on this. Let's talk about reflection and refraction of waves. So now, before we talked about what happens if 2 waves or wave meet, or maybe more waves meet each other at the same spot at the same time in space. But what happens if a wave meets a surface or some kind of interface between 2 media? So let's say we have a wall and a sound wave. So as a sound wave hits, this is actually a longitudinal wave, so it would be, yeah, maybe we should represent it like that if you like. And this sound wave, part of it would probably go through the wall, but some of it could be reflected from the wall, and it could happen that all of it is absorbed. If I have a special type of dark or absorbing surface, then light could be completely absorbed, or sound wave as well, more absorption would happen. But let's say we have a reflection happening here from the surface. Those surfaces are the type of surfaces, this is the type of surface that reflects sound wave. So we will have reflected ray that is this way. Now there's only one way this ray could be reflected. And how did I know it was this way? Well, because in my mind, what I do is I'm trying to draw this normal to the surface. Normal means perpendicular. So if you draw normal to the surface, if you want, you can do it both on both sides of the medium. Then the incident ray, this is incident ray, incident, and reflected ray, this is reflected, will happen to have the same angles between normal and this ray. So we will have angle, this is angle of incidence, and this is angle of reflection. So angle of incidence always equals to the angle of reflection. So in nature, every time you have some reflection from a surface, it happens in such a way that this law is obeyed. So if we have surface like that, for example, and this would be, I guess, normal because it's perpendicular to the surface, like that, this dotted line, and let's say this wave is falling on a surface at this angle. This is incident ray, incident wave. Then this red one representing the reflected one would be like that, because this angle here has to be equal to the second reflected angle of reflection. So angle of incidence here, the first angle, has to be equal to angle of reflection, the second angle. So every time I give you a wave that's incident on the surface, you can reconstruct the reflected wave by just drawing a normal to the surface and then making sure that it looks like the angles are approximately the same. You could make a sketch, I guess. And this is what this diagram is representing as well here. So this is angle of incidence, this is angle of reflection, and those two angles are always equal. We could have a air and glass, and we know that glass is transparent to visible light as well, so some of the light does reflect from the surface, but the rest of the light could go through the surface. So which way would it go? That's the question. So my question is, would it just carry on going this way, or would it bend? Well, turns out that we would always have this wave the wave that goes through the surface to the second medium would not only just change the speed of its motion, propagation, but it also would change direction. So this transmitted wave would not carry on the straight line. If the speed is changing, if the light happens to slow down, turns out that if the light happens to slow down in that second medium, then this transmitted wave would bend in such a way that its angle is getting smaller with the normal. So this is a scenario we would have if light slows down or wave slows down in the second medium. If the transmitted wave slows down, then we have this wave bending towards the normal. Now, what happens if this reflected wave speeds up? So now again we have light transmitted through it, but let's say in this case, let's say it's not air, but let's pretend it's I don't know, air, let it be air again, but wall, and let it be concrete wall, and let it be sound waves. We know that sound waves move faster in solids than gas or air, so sound wave would speed up. So it turns out that when transmitted wave speeds up, it will bend away from the normal, so it will not carry on a straight line. No, because it would speed up. If its speed changes, then it no longer carries on a straight line. But would it bend towards the normal or away from the normal? Well, because it's moving faster, it will bend away from the normal, so it would go like that. So this angle here is bigger than incident angle. So refracted angle, or angle of refraction, is bigger than angle of incidence if it's speeding up, if the wave, transmitted wave, is moving faster in the second medium. Now, it might be difficult to memorize it, and you would have to memorize it before the exam. So I have some diagram here to help you a bit. One way you could try to think of it is a marching band or a car that's entering a mud. So let's consider this car analogy first. So let's say we have a surface here, and on this side we have a pavement on which the car has no difficulty to traveling, and here let's say we have a mud or a different type of surface, or water if you like. So when a car is entering this surface, let's draw a car, those are wheels. So when a car is approaching this surface like that, the first part of the car that reaches it is the front wheel, this one here. And what will happen is that it will be slowed down by the surface because it moves slowly in the mud. And when this wheel has traveled a bit of a distance, the second wheel, meanwhile, was still moving fast, and it would have traveled a bit farther. Let me try it again. Sometimes, to understand it better, it's in some situations it helps to visualize it. If we think of it helps to visualize it better if we imagine a car that's entering an interface between pavement, for example, and mud. So as the car enters the mud, it will probably slow down. And the first part of the car that's entering the mud is this wheel here. I will do it in red. So this wheel enters the mud first, and it carries on moving, but it would be slower. And the wheel on the other side of the car is still moving fast. So when this left wheel has traveled a tiny bit of distance, the other wheel has traveled bigger distance from here to here. And this turns the car as well. So then when both of the wheels are inside the mud, they will carry on at the same slow rate. But you can see the car has turned a bit. So it was going that way, and now it's going this way. And this is how you can think of the waves as well. As they fall on the surface, they bend in such a way that if it's slower, if it travels in the second medium at a slower rate, then it bends towards the normal. Another visual maybe help could be to think of a marching band like that. And as they go closer to the surface, you know that this person gets slowed down more than the others. The others don't get slowed down because they are still moving in a faster surface. But in the mud, the first person struggles to move as fast, while this person here at the end has moved a bigger distance. And the same is true for people in between. And eventually you would have all of the marching band turning that way. So we would have light or sound wave traveling this way, then bending a bit towards the normal if it slows down. And if it speeds up, it would turn the other way around. Alright, so let's move on. here's some examples, and I'm asking you to draw reflected waves for the following waves, and also refracted ones. So reflected and refracted waves. To draw them or make a sketch. And please remember to pause the video and think about it. At least try to visualize what would happen. Okay, I hope you did that. And now play the video and see if we got it right. So this first example, this is incident ray. This one is incident ray. And we know that light always reflects at the same angle from the surface, from the normal. So whatever the incident angle was, the reflected angle has to be the same. The only way this could happen is if it reflects, let me see, so 2 by 1, right? So I will do 1 by 2. So if the ray goes like that, or you could just do it by eye, you don't have to be exact. So this is reflected wave. Let's do a reflected wave for the second one as well. I will do it in green. So I know that this angle of incidence has to be equal to angle of reflection here. So it has to be reflected in such a way that those angles will end up being the same. Or one way I could think of it is 1, 2, 3, 4, 5. Every time I go 5 right, I go 2 up. So I would go 5 left, 1, 2, 3, 4, 5, and 2 up. And that way I'm mapping this triangle like that. So this is a reflected wave. Or I could just sketch the graph by eye. Again, in the third diagram here, I will have reflected wave. That's approximately, before I draw reflected wave, I would recommend drawing the normal. And then I'm making sure that I draw the reflected wave in such a way that this angle here is equal to this angle. So something like that. So this is good enough, maybe a bit more like that. So you might have multiple choice questions on that in the exam or homework. And you have to choose the one that's best describing the reflected wave. So this is law of reflection. Now we want to do the second part, and we want to draw refracted wave. So refracted wave, for this one, we know that light doesn't just carry on a straight line as it's transmitted to the second medium, but it bends. Now, which way does it bend? It says here that it's entering a medium where its speed is slower. So if it slows down, remember, if it slows down, it bends towards the normal. Think about car entering a mud, if you like. So we should remember that if it slows down, it bends towards the normal. So maybe something like that. There's a formula to find this angle. It's not too complicated, but we are not covering this. So all I need from you is just sketch it. Do your best to sketch it. We don't need to calculate the exact value of this angle. It involves trigonometry as well. And the second one would be, this is incident ray. So incident ray would not be carrying on a straight line. The wave speeds up. So if it enters a medium where its speed is higher, it will bend away from the normal. So let me do it in red. So away from the normal, this is normal, right? This is normal, so away from the normal means that way. So the reflected wave would bend this way. Refracted wave would bend this way. And in the third one, again, we have this incident ray, and a reflected wave is here, and refracted wave would bend a wave from the normal because it's a faster medium, means away from the normal. Normal is this, so away from the normal, this would happen without any bending, but bends away from the normal means this way. So yeah, I hope you see it. So this doesn't carry on a straight line, but bends a bit. Maybe I should do it in black. So like that. Okay. So it's not difficult as long as you remember which way it bends. And reflected ray as well, it's really easy to draw it by eye. So let's now talk about mechanical waves in general. So mechanical waves, we mentioned it earlier as well, but it's basically a type of waves that require a medium, and it could be longitudinal waves or transverse waves, and it could travel in solids, gas, or liquids. And so the way they, for example, how do we produce them? We can produce, what could be source of that? The source of that could be rock that fell in the water, or it could be vocal cords is what I'm using now, producing sound. And also it could be due to earthquakes, ropes in the string, and so on and so on. And what we need to maybe understand that we could have mechanical waves that are both transverse or longitudinal. Transverse wave example would be rope we made in a the wave that we made in a rope, and longitudinal, the best example of that is sound, which we will cover in more depth later slides. So a human ear, for example, can distinguish between those two frequencies, 20 Hz and 20 kHz. And you think it's a big range, but dogs actually can hear even better, up to 60,000 Hz. So really high frequencies or high pitch sounds, dogs can still hear it. And the bats and dolphins are even capable of hearing even higher pitch or higher frequency sounds. So in fact, that's how bats can navigate in the dark. They cannot see, but they emit those waves, basically sound waves that we cannot hear. We call them ultrasonic waves. And those ultrasonic frequencies are slightly higher than the frequencies that our ears can perceive and distinguish as sound. So we don't hear it, but the bats and dolphins, for example, can. And as this wave is reflected from the objects in front of them, the bats can visualize those objects, so they see objects using sound, if it makes sense. So they can avoid that object when flying. And the same for dolphins, they could map the surrounding by just emitting those ultrasounds and getting echoes back from those surfaces, and they would know the distance between themselves and those objects by just figuring out how long it took the sound, how long it took to get to them. This ultrasonic waves, ultrasonic frequencies. And doctors are also using those frequencies to examine the baby development, for example, and there's lots of applications. And ultrasonic waves are better than sound waves for example, to examine the baby, because it's outside the spectrum that we can hear, and we cannot really, it's less annoying. And also another reason would be because the bigger the frequency, the better the definition or resolution, so we can resolve something better. So microscopes use the higher frequencies microscopes use, the better the resolution of the object that we are observing. We'll probably talk more about that at some point. So we would have sound waves giving us some kind of image, but ultrasounds are even better because they have even higher frequencies. So infrared and ultraviolet are the edges of the visible spectrum where we can see, we struggle to see at those ends of visible spectrum. The same with sound waves. We have ultrasonic edge and infrasonic edge of the audible sound waves, and we can no longer hear them. And by the way, small children have more sensitive ears to high pitch noises, so they can distinguish some sounds better. They perceive it better than grown-ups. With age, you just lose ability to distinguish higher pitches, so they hear a bit differently from grown-ups. For example, they would be more annoyed to hear some specific frequencies. So let's talk about resonance, more or less. We will talk much more about resonance when we move on to electromagnetic waves. But now I want to just introduce you to the idea and give you an idea behind resonance. So let's imagine a fishing rod that's on a lake, or let's say sea. So it's this diagram A here. And let's say a big wave is coming towards it, and the wavelength of this wave is huge, 20 meters. The length of this boat is only 2 meters. And you probably would agree with me that this boat wouldn't feel a difference. So I would just carry on fishing without even noticing this wave much. But if the wave that's coming in will happen to have a frequency that's closer to the length of the boat, like 4 meters, and even worse, 2 meters, then I would notice this more, because the boat would start oscillating more. You can see here a visual representation of that. But if the frequency is too high or wavelength is too small, then I would have no influence on the boat. So the boat would just carry on being horizontal, and I would just carry on fishing. So this example illustrates that in order for this receiver, or we could think of a boat as a detector that detects waves, for example, it's more efficient at detecting waves that are at the same frequency range or wavelength range as the boat itself. So the length of the boat can make a difference. So if the receiver and the source have the same frequencies, then we have a resonance happening. So the boat resonates with the waves and is affected by the waves more. And this boat has its natural frequency or natural wavelengths would be 2 meters. So the incoming wave would have to be 2 meters to be able to be detected by the boat. Or natural frequency that corresponds to whatever that 2 meters is. I guess speed of that wave divided by the wavelengths, right? Because V equals lambda F. So if I know wavelengths and speed of the wave, I could find natural frequency of the boat. So this is important to understand, because later on we will talk about resonance in electromagnetic waves as well, and we will try to make analogy between those two as well. So resonance is something sometimes we want to avoid, and sometimes we want it in order to achieve something. For example, if you are swinging a child a child is on a swing and we try to push them. If we push them in a random order, you wouldn't be helping this kid to oscillate, right? We would be sometimes helping them speed up, but sometimes slowing them down. So we need to apply this force at a certain time or with a certain frequency. I am guessing resonant frequency, which would correspond to whatever the natural frequency of that oscillation is. So if you want to achieve the result, you have to pick the right frequency. Or resonance here is helping you to swing this child um, on a swing. But what about musical instruments? Again, we design violins in such a way that resonance happens here to produce beautiful sounds, and there is lots of different designs of different musical instruments that take into consideration this resonance. So those strings oscillate at a certain frequency, right? So we want the shape of this violin to help us, not reduce this effect. This source of wind, in this case, is pushing the bridge at a constant resonant frequency. Then you could damage the bridge. So you should have engineers are trying to create bridges that prevent that. So to make sure they don't they prevent the bridges from resonating with the wind. The same is true for houses. So when you have an earthquake, you could see one house falling down and the other next to it being not affected by the earthquake, because that specific house happened to resonate with the wavelengths or frequency of the earthquake. Earthquake happened to have a frequency that it corresponded to the natural frequency of that building. And now let's talk about loudness and pitch of sound waves. So what is sound waves? We talked about it. It's just disturbance that travels in space, and it's carrying energy. So for example, if this bell rings, its surface oscillates and produces oscillation of the surrounding air with the same frequency, and we will have those rarefications and compressions in air that propagate in space. And I think last time I attached a video on that, so it would be useful to have a look at how this longitudinal wave propagates in space. So those rarefications and compressions travel in space, or pressure waves travel in space, and they eventually reach ears, which happen to be sensitive to those specific frequencies, and they perceive it as sound. And those impulses are eventually converted to some nerve. Those oscillation of my air drum is eventually converted to the nerve impulse that is delivered to my brain that perceives it as sound if it's within the audible range of frequencies. So loudness, what I perceive as loudness is actually energy of the wave. The more energetic, the louder the wave seems to be, and it has to do with amplitude. So it turns out that the bigger the amplitude, the more energy of the wave, and therefore the louder it will seem to me. Pitch, on the other hand, is something that's perceived by my brain as when I have different frequencies. So higher frequency is corresponds to high pitch, and if I have a lower frequency wave, my brain perceives it as a low pitch sound. So here's a good example. For example, so those two would have different frequencies or wavelengths, those longitudinal sound waves. But this one and this one, for example, would have the same wavelengths but different amplitudes. So here different pitch, here different loudness. Now let's talk about speed of sound waves. We talked about how sound was traveling faster in liquids than in gases, or it's faster in solids than in liquids. And the reason is because, for example, in solids we have more restorative forces. So when you deform a molecule, it tends to be restored. The force that's restoring it is bigger. So this wave would be pushed faster through the solid. And if you have a hot air and cold air, turns out that sound propagates faster in hot air because its molecules in hot air move faster and they're more capable to transfer energy to the next molecule and so on. So this transfer of energy happens faster. That's it really. That's why it propagates faster in hot air. And speed of sound, it's interesting, but we briefly talked about it, but I want to talk more about this. This formula here shows me that speed of the wave is equal to wavelengths multiplied by frequency, right? So speed of wave only depends on the medium. For example, whether it's a gas or a liquid or solid or what kind of solid it is, temperature and so on. So it's characteristics of the medium that determines the speed of sound. And we talked about how wave changes its speed when it enters a different medium. So, for example, its speed could go down, right? So in this equation, we can see that if speed goes down, then something else has to change. Turns out that frequency doesn't change. What changes is wavelengths. So wavelengths would be less, but frequency is what determines the color or pitch, which stays the same. Let's now talk about sound insulators and echoes. So we talked about echoes when we talked about beds, but let me mention just one more thing. So when a sound is reflected, sound wave is reflected, or another type of wave is reflected from a surface, some of it probably could be absorbed as well, but some of it reflected back to my ear here. If this distance is too small, then the wave, the reflected wave and the sound wave produced by me wouldn't have such a big difference in time, and then I wouldn't be able to distinguish them as two separate sounds. But turns out that if this time is bigger than 0.1 second or 1 millisecond, then I can distinguish those two as separate sounds. That's why you hear echoes in big buildings, because this delay in time between this reflected and the original sound wave is big enough for you to distinguish. And so one more thing I want to mention is directional microphones. So some microphones are using this reflection of sound waves to target all of those waves, to direct all of those waves into one spot where they are being received or detected. And keep in mind that at each point the law of reflection is obeyed, because if you draw a normal to the surface, this is incident ray and this is reflected wave. So design of those are helping reflect it in the right direction so that it's focused on one point. So let me do one more example. So this ray or wave as well, if it's sound wave, it could be light as well, is reflected in such a way that we redirect it into the middle here, like that. So this microphone would function much better than if it didn't have this part that's reflecting sound waves. And one more thing I want to mention is, remember we talked about insulators and how air pockets would prevent heat transfer by conduction. So turns out that air is also good for insulating sound. So if we have air pocket inside the wood, for example, or any kind of concrete, so sound waves that reach those air pockets are reflected back and forward in several times within the air pocket and eventually dissipated. So it's good absorbent of sound waves as well. One more thing I forgot to mention as well earlier is, remember how we said that if light is incident on a surface, it will be reflected, for example, this way, right? But what happens if light is incident like that, with a normally to the surface or at a right angle? Then reflected light would also be exactly upward, right? So angle of incidence is 0, so angle of reflection is also 0. And turns out that if any of it goes through the surface, this wave would also not be bending. It would just carry on a straight line. So this is the only case when we don't have all those sound wave or light waves or those waves, whatever they are, although they still speed up in the second medium, they don't change direction. So when sound or light waves are incident at a right angle, like that, to the surface, then they carry on a straight line.